confused a little bit about symmetry, and the point of this is not really to get good at symmetry, but we were trying to figure out how to identify homotopic versus enantiotopic versus diastereotopic groups, which I know is a subject if you're in 455 or 555 that you encounter, and I know the way it's explained in a lot of introductory OChem texts is not that helpful. So I'm going to try to show you what little I know about symmetry. We'll go through it a little bit more systematically, and I'll try to re-explain stuff that I didn't do very well on Friday. So, symmetry operations. You've got rotational axes. So in this trigonal planar geometry, often systems of high symmetry have multiple symmetry elements in them. For example, this trigonal planar molecule has a C3 axis, which means that you rotate by 120 degrees, and then the coordinates of the molecule remain unchanged. And that's a really important definition. In symmetry, it's not enough to say, oh, well, if I move the molecule from here to here and flip it over, it's the same thing. No, for symmetry the precise rules of symmetry are you move the atoms, but if you look at the list of coordinates for the molecule, after the symmetry operation, the coordinates are all the same, even though you've traded one hydrogen with another. Does that sort of make sense? So after a C3 rotation, this hydrogen will be here, this hydrogen will be here, but the actual XYZ coordinates of the molecule remain the same. Similarly, there are C2 axes. If you run an axis in the plane of the page through this MH bond and then you rotate 180 degrees, these two hydrogens trade places. So various rotational axes, and then mirror planes, and we usually call those sigma for reasons I don't know. This trigonal planar molecule has a sigma mirror plane in the plane of each of these MH bonds. Similarly, and I've tried to highlight in purple which line this mirror plane coincides with. In this case, the mirror plane is in the plane of the page. This hydrogen reflects into that one. You can run a mirror plane through this MH bond, and this hydrogen reflects into that one. You see that? And same thing over there. And here's another example of symmetry in a tetrahedral geometry. Here's a MH3Y group, where Y is something not hydrogen, and you've got another C3 axis here, and you've got various mirror planes. Notably, you don't have the C2 axes there anymore because the hydrogen breaks the symmetry. You can use symmetry elements to assign point groups. That's where I get off and don't care at all anymore. I get off the train at that point. More power to you if you do care about it, but and maybe someday I will care about it and learn. Okay, so the CN axes are called proper rotations. And this is an example of a proper rotation. The axis is perpendicular to the page coming out at you, and if we rotate around that axis by 180 degrees, sort of steering wheel action, the XYZ coordinates are the same, even though we've traded this OH group and moved it here. In other words, the coordinates are the same, the structures are indistinguishable. More complicated is the concept of improper rotation, because it's two things. You've got to do a CN rotation followed by a mirror plane, but the mirror plane has to be perpendicular to the CN axis. I didn't make up the rules, but that's what it is. So here's an example of the lowest the simplest SN improper rotation. This is rotation around a C1 axis. That's just 360 degrees. That's a no-brainer. That's like, of course, you turn around and you're exactly the same thing. But it turns out to see it correctly, you have to choose the right axis. So in this case, we're looking at isopropanol, or rubbing alcohol. the OH and the CH and COH bonds are in the plane of the page. One methyl is coming out at you, another methyl is back away from you. We can also look at this molecule from the side, and that's what I've drawn down here. The gray line represents the plane of the page. From our perspective over here with Darth Sidious's eyes, we would see the OH coming out toward us, and then the CH bond going back into the plane, going back away from us. So the axis we're going to consider is one that goes through this carbon and is perpendicular to the page, and you rotate by 360 degrees all the way around. Of course, it's the same thing, boring. But the point is not, is it the same thing after rotation, 360 degrees? The point is it the same thing after both the 360 degree rotation and the mirror plane? So I've tried to draw a mirror plane. This mirror is in the plane of the page, so it contains the OH and H groups. The methyl is above the mirror, and the other methyl with the dash is below the mirror. Similarly, if we were to look at this on the side, this is what we would see. Here is the mirror. And you can see that if we reflect everything above the mirror, below the mirror, you guys know that the mirror operation is a front to back kind of thing. The stuff that is farthest, the stuff that is in front, closest, I'm not going to say that right, so we'll just keep on going. We all know what a mirror is, right? Ish, yes, okay. Right, what do I want to, anyway. It is a front to back, but all of a sudden I said that and I'm not seeing it anymore, but anybody want to care to explain that, or are we just okay with what a mirror does? All right, that's fine. So the mirror contains the oxygen and the hydrogen, and it exchanges the positions of these methyl groups. If we were to label this one A and this one B, after the mirror, this one is B and this one is A. And yet, the XYZ coordinates are still identical. And so, by definition, this molecule is the same as its mirror image and is not chiral. So that's what an S1 axis is. And any molecule that has an S1 axis is its own mirror image and is therefore not chiral, right? It gets a little more complicated when you do improper rotations where n is greater than 1. And this is tricky and sort of what I got confused on. So I'm going to take you through an S2 rotation just in the same way as we did the S1. So here is our 2,3-butanol molecule of indicated stereochemistry. Again, our axis of rotation is going to be perpendicular to the page and sort of bisecting the bond between these two carbons. We're also going to have below, if you would like it, a side view where the gray line indicates the page, and we're viewing this molecule from the left-hand side as shown here. Such that with the carbon in the front, the OH group is coming out of the page, the carbon in the back, the OH group is going into the page. So remember that the point of the improper rotation is you only check and see if it's identical after you do both the rotation and the mirror plane. So 180-degree rotation here swings this OH group around to this position and this OH group around to that position. So can you see where we get that from? This is just steering wheel action, right? Everybody okay with that? Similarly, if you do that here, you take the methyl group in the back and pull it forward to become the methyl group in the front. Notice that after that C2 rotation, the XYZ coordinates are not identical. The OH group that's up here is down instead of up. But in the case of the improper rotation, after we've done C2, done our C2 axis, we then reflect through the plane that is perpendicular to that C2 axis. That is the page, and the page is here. So if we notice that all of the carbon-carbon bonds are in the mirror, plane of the mirror, so they don't change at all, this OH group, which is below the page, would get reflected by the mirror to be above the page, and this OH group, which is above the page, would get reflected by the mirror to be below the page. That's when we get here. We can do a similar thing here where to get from this structure to this one. And after those two operations, and only after those two operations, do we get a molecule that is identical in XYZ coordinates to what we've got there. Okay, any questions you want to ask about that? Anything that's difficult to see?
Could you go over just like the coordinates part again? Because like the mirror reflection part makes sense.
Yeah.
Yeah.
So in order for a molecule to have an improper rotation axis, you check the starting structure and the ending structure, and you confirm that the XYZ coordinates are all the same. You've interchanged atoms, but remember, we can't really, if these are all carbons and everything and so on, we can't tell the difference between this OH group and that OH group. In the sense, yeah. So if you compare XYZ coordinates before and after, they're all the same. Yep. Now, I agree with you that it's still the same molecule if I spin it around 180 degrees. We're not changing connectivity, but that's not what symmetry means. Symmetry is, are the coordinates all the same? It's a math thing. Probably involves matrices, I don't know. Yeah.
I can see the S1 and the S2. How would you do an S3 or 5?
Ah, dang, why did you do that? I knew someone was going to ask that. How would you do an S3 or an S5? Okay, well, I just happened to have Googled the S3. So before, I'm telling you, one of the skills you get in grad school to become an independent scientist is not that you know everything, but you know where to look and where to recognize an answer when you found one. My one superpower, the one thing I'm good at, is asking Google the right questions. So this trigonal, what do we call this symmetry? Something, yeah. Okay. So I don't know if that should be phosphorus or some other kind of metal. It probably is platinum. I don't know. Now I'm going to need to Google it again. But
it's not a big deal if it's phosphorus or platinum.
Okay.
It's a placeholder.
Right. What? Yeah, because phosphorus makes PF6, right? So, but that's not 6. That's 5. I'm going to have to Google something now. PCl5, does that exist? Yes, it apparently exists, so we're fine. We'll say that's phosphorus, whatever, I'm sorry. So the S3, yes, yeah, you can have it back. I was just going to keep drawing and you guys are going to have to imagine. All right, so the S3 axis, thank you for that, is right here. It contains the two axial chloro groups, and you start with a C3 axis here, that's rotation by 120 degrees, and then the mirror plane through which you reflect contains all of those equatorial phosphorus Cl bonds.
So is that different from just a normal C3 rotation? Because this looks like it has C3 symmetry as well.
It does, yeah,
Okay.
yeah. Those things can coexist, yeah. What would break that symmetry, it would still be a C3 axis, but it wouldn't be an S3 axis if we change that to something else. Because then on reflection, you'd have different coordinates. All right. You asked for the 5. Cyclopentadienyl anion, all of those carbons are identical. Presumably you have an axis here, which would be a C5 axis, that is divide by 360 divided by 5, whatever that is. Maths, 12, I don't know. Why don't I know?
12 times 6, 72.
Okay, thank you. Arithmetic is not good, right? 72 degrees. And then again, the plane of the page would be the mirror plane. And so, yeah, you've got an S5 axis there.
Makes sense.
But any molecule that has an SN axis is by definition its own mirror image, because the improper rotation is you just spun it around a little bit, which doesn't change the connectivity, and then you do the mirror image. So if you have a SN axis, you cannot be chiral. Okay, so we're using these symmetry elements now to identify homotopic versus enantiotopic groups. And we said last time, and this is probably the easiest to see, that groups that are interconvertible by a CN axis are homotopic, which means they're chemically and magnetically equivalent always, even in a chiral environment. And so we went through how through an axis of rotation that's in the plane of the page and goes through this carbon, we can spin this molecule around and HA and HB interchange places. Similarly, through this C2 axis indicated here, again in the plane of the page, bisecting these two carbons, going through that carbon, the two methyl groups interchange places. Also the phenyl groups interchange places. So it is correct to say these methyl groups are homotopic. They are magnetically and chemically equivalent always, even in a chiral environment. Similarly, these phenyl groups are homotopic. And then we can also apply this reasoning to faces of planar molecules. There's a C2 axis here that coincides with the carbon-oxygen bond. And if you rotate around that, the methyl group here becomes this methyl group there. That means that this perspective, the top face of the ketone and the bottom face of the ketone, are homotopic and will always be the same even in a chiral environment. So you would not expect an enzyme to be able to have a preference for reducing this ketone from this side versus that side, because the faces are identical even in a chiral environment. All right, a little bit harder is enantiotopic. So that's where we got derailed last time. So I'm going to make another attempt. Enantiotopic groups or faces are interconvertible by an SN axis, where n can be anything greater than or equal to 1. And these groups are chemically, and remember, the SN axis is a CN axis plus a mirror plane rotation. They are chemically and magnetically equivalent, except in a chiral environment. The reason you want to know the difference between homotopic and enantiotopic groups is because you can distinguish with a chiral reagent between two enantiotopic groups, but you cannot distinguish with a chiral reagent between two homotopic groups. So you want to know this so that when you go to your postdoc advisor and you say, yeah, I think we ought to try using this chiral ligand, and that way we can tell the difference between these two methyl groups, and you're going to look silly because they're homotopic, not enantiotopic. So let's just take the example that we did before of this molecule. We would say that these two OH groups, this one A and this one B, we would say that those two OH groups are enantiotopic because, as I've shown you, you can interchange them by a C2 operation, which takes HA and puts it OHA there and puts OHB there, followed by a mirror plane, and that C2 operation, remember, is over this axis, and then the mirror plane is the plane of the page, which interchanges, I don't like that, let's try again. And that mirror plane will bring OHB up above the page and OHA below the page, which interconverts and trades the positions of OHA and B. Okay? Yes?
Does enantiotopic or homotopicity take precedence? So like if you have both SN and CN symmetry, do we say it's homeotopic or enantiotopic?
That's a good question. If you've got both, no, what makes these two methyl groups homotopic is that they're interchangeable only by a C2 axis. You'll notice that they're not, it wouldn't be, you'd need an axis perpendicular to that C2 axis to make it an improper rotation. But even if you want to say, oh, well, if I have a mirror plane in the plane of the page, does that fully interchange these? No, because the mirror plane doesn't reflect this one and that one into equal positions. So yeah, if you have an SN axis, they're going to be enantiotopic, not homotopic.
So the example you showed us for S3 was both C3 and S3.
Yes.
Would that be homeotopic or enantiotopic?
So, that's a tough question now. So you have a C3 axis, and you also have S3 symmetry because of the mirror plane. So these two groups, because they interchange via the C3 axis, are they enantiotopic? I don't know. I struggle with chirality. Yeah, I don't actually know. I don't think that's...
If you don't know, it won't be on the test. So
No, if I don't know, it won't be on the test. And it's possible that the rules that they've told you in your text work for typical organic molecules where you're bonded to 4 different things. If you replace, by our definition, these CL groups would be enantiotopic, but if you replace one versus the other, you don't get 2 different enantiomers, so that tells me they're actually not. Yeah. All right, so I don't know, but you're going to be dealing with that in organic molecules, not in more complicated inorganic contexts. Okay, so anything else we need to say about enantiotopic groups? I think the example we were doing at the end of class last time was something like this, HA and HB. They are not homotopic because if you they're not homotopic because there's no C2 axis that interchanges them. You can try, let's try to do a C2 axis here and rotate it, but when you do that, I mean, of course it's the same molecule, but notice that the coordinates are different. The XYZ coordinates are different. The chloro's in a different place. So there's no, so those two hydrogens are not homotopic because you can't interchange them via a CN axis. However, you can interchange them via an S1 axis. That is, do a 360-degree rotation here to get the same thing, boring. And then the mirror plane would be the plane of the page. And at that point, if you apply the mirror plane, the Cl and the Cc bonds remain unchanged. Hb gets reflected up above the page, and HA gets reflected down below the page. We have fully traded the positions of HA and HB through this, through these two symmetry operations, and the XYZ coordinates are the same. Therefore, those two groups are enantiotopic. What that means is that a chiral reagent or a protein can distinguish between HA and HB. And in fact, we can actually have different names for these two hydrogens to reflect the fact that they're different in chiral environments. We'll do an experiment where we replace hydrogen A. We'll do a thought experiment where we replace hydrogen A by something else. We'll call it Z, and Z is just, you know, whatever it is, it has higher priority than hydrogen. Let's say we imagine it to be deuterium. And then we assign stereochemistry. We would say, if that becomes something different than hydrogen, it would be R. So we're going to call that hydrogen pro-R. And similarly, you could say, if we replaced HB with something that is higher priority than hydrogen, but only just barely, and we assigned stereochemistry in the usual way, from group 1 to 2 to 3, and it looks like it's clockwise, except your hydrogen, your lowest priority group is up instead of down, therefore we would say it's S, and similarly we will call HB a pro-S group. And a chiral enzyme, a chiral reagent, can distinguish between the pro-R and the pro-S protons. Pro meaning before. It's not chiral yet, it's not a stereocenter yet, but a chiral reagent can easily tell the difference between the two.
And their equivalents are not the same. The HA and the HB.
They are, HA and HB are chemically and magnetically equivalent with this exception. If you're in a chiral...
In this compound.
Yes.
Chlorine.
Yes.
They are different. in this compound, are they the same? HA and HB.
You want me to say yes or no, but I can't. I say yes, except.
Then-
Yes, except if I put, as I've shown them here, yes, they are identical. Now I'm going to have a chiral Pac-Man protein, which has lots of stereocenters in it. And now we're going to put those, oh, I didn't want that, I just wanted to paste. Now we're going to put that molecule in the protein, and now the protein can tell the difference between the two. Now they are no longer identical. So they are equivalent, HA and HB are equivalent in a non-chiral environment. But now because they are in a chiral environment, they are no longer equivalent.
Is there any effects of the chlorine on any of the hydrogen?
Sorry, what about the chlorine?
Is there
in the-
any effects of the chlorine on any of the proton electronegative? Would it have effect maybe like the sheets any of the proton?
Okay, so you're asking the effect of this, of the chloro being electronegative, will it have a different effect on these two hydrogens?
Yes, and maybe make one-
Not in a chiral environment. I'm sorry, dang it. Over here, remember, they're identical. If it's not in a chiral environment, they are identical. Therefore, this chloro has the same effect on this hydrogen and that hydrogen. They have to have the same chemical shift. They have to. When you put it in a chiral environment, they are no longer equivalent, so they don't have to have the same chemical shift. Yeah.
Would that chiral environment caveat go for if the chiral center is on the same molecule as well? Like, let's say that Cl was replaced by a chiral center. Would that change the way that we would view HB and HA?
Right. If the chiral environment is in the molecule itself, then we actually don't use the word enantiotopic anymore. Instead, we use diastereotopic, which we can, which we're going to get in just a second. We can also talk about enantiotopic faces of planar groups. So let's just do this ketone that's only slightly less that's just a little bit less symmetric than the acetone that we did before. This molecule has a top face and a bottom face. And the top face and the bottom face are exchangeable via an S1 axis. And the S1 axis is here. Sorry. The S1 axis is here. You rotate by 360 degrees and then you reflect through this mirror plane, and what was on the top is now on the bottom. Now, if you think about this molecule and you're looking at it from the top, the methyl group's on your right and the ethyl group's on your left, right? But if you put yourself looking at it from the bottom, now the methyl group's on your left and the ethyl group's on your right, okay? So the two faces are exchangeable by an S1 axis. They're not exchangeable by a C2 axis. In other words, if I just flip this molecule over, do a C2 axis, the coordinates are not identical. So we call these enantiotopic faces. And what this means is a chiral, why can't I spell enantiotopic? Enantiotopic. A chiral reagent or a protein can distinguish the top face from the bottom face. And we have words to describe, similar to pro-R and pro-S, we have words to describe these two enantiotopic faces. And to see how to do this, you simply assign priority via the regular stereochemistry rules to each of these groups. And then you draw an arrow from 1 to 2, from 2 to 3, and from 3 back to 1. From the top face, if I look at that, that is counterclockwise. And so I'm going to call this the psi face. I don't know, I mean, it looks like we should call it the C face, but chemists don't say that. They call it the psi face. So it's a long I. The bottom, though, if you think about looking at this from underneath, it's going to be clockwise. And so we'll call this the ray face. The R and the S have the regular stereochemical meaning. And those two faces are enantiotopic, meaning a chiral reducing reagent, for example, could selectively deliver a hydride from the psi face and to give you one enantiomer as a product, or from the ray face to give you the other enantiomer as a product. All right.
Is this how we get like enantioselectivity in like reactions and stuff?
Is this how you get enantioselectivity in reactions? Yes. Yep.
Why do you rotate 360? And rotating 360, will it not take it back to the same spot?
It does. The simplest improper rotation axis is a 360-degree rotation followed by a mirror plane. I guess the people that invented the symmetry rules do that because they want to show a connection between just a regular mirror plane reflection and then one in which you spin around by less than 360 degrees into a mirror plane. So if you see S1 axis, you can totally ignore that. What that means is a C1 operation followed by a mirror plane. But a C1 operation is basically what we would call an identity operation. It has to be the same thing, right? And so we can drop it out. If we were doing linear algebra, this were a matrix to do the transformation, it would be an identity matrix. You'd multiply. It would just give you the same thing. All right. So lastly, let's talk. So in my mind, homotopic and enantiotopic, that distinction is the hardest one. I don't think diastereotopic's very hard, though I think it's a concept that for in introductory OChem courses it becomes difficult. But this one is much, I think, easier. Why can't I spell? This one is much easier to see. Diastereotopic. There we go. So diastereotopic groups, and this is why it's easy, they cannot be interchanged by a symmetry operation. They don't have the C2 axis or the SN axis or whatnot, and they are always different. Chemically, magnetically, etc. Worlds without end. So let's talk about diastereotopic groups. If you have a chiral molecule, the molecule or a molecule with a stereocenter, two CH2 protons are diastereotopic. Okay? Do you see how there isn't a mirror plane that interchanges HA and HB completely? Because the mirror plane would also move the OH group. So there's no improper rotation that will interchange and give you identical XYZ coordinates. So those are diastereotopic. They are different. Now, that means even a boring non-chiral reagent could selectively remove one of these protons versus the other. And so this is why diastereoselectivity is less exciting to people than enantioselectivity, because you expect diastereoselectivity to be a thing. There's no reason, for example, the rate of the chemical reaction of this proton being removed versus that proton being removed could be totally different. And it's unsurprising because those two protons are chemically and magnetically different. Similarly, we're going to learn a little bit later on as we talk about, I don't have my watch. Are we out of time?
Yeah.
Oh, you guys are just going to let me keep on talking, right? Okay. All right. We will end there. I was going to talk about diastereotopic faces of ketones. The concept's not that hard. So we'll just end the lecture now.